Welcome student. The octahedral complex only sigma interaction we will discuss in different way. The previous lecture, which includes the write-up of 4 steps to construct MOED for octahedral complexes, here with different perspective, with different thinking angle, we are going to obtain the octahedral complex, and this is for only sigma interaction. I am Dr. Devak Pandya, Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. The points to discuss: first, sigma bonding in octahedral complexes. Then different steps involved in the formation of sigma molecular orbitals in octahedral complexes. Step 1, to make a selection of metal ion orbital suitable for sigma bonding. Step 2, to determine ligand p sigma orbital combinations. And step 3, formation of sigma molecular orbitals in octahedral complexes. Last not least, pictorial representation of the formation of MOs. The first point, sigma bonding in octahedral complexes. Let us consider an octahedral complex in which the central metal ion is surrounded octahedrali by 6 ligands like L1, L2, L3, L4, L5 and L6. A common example for this is hexaamino cobalt plus 3 complex. So here you can see that the central metal ion is over here. This is ligand 1, ligand 2, ligand 3, ligand 4 in a planar position, ligand 5 and ligand 6 on axial position, and that interact with central metal ion forming sigma 1, sigma 2, sigma 3, sigma 4, sigma 5 and sigma 6 bond. Instead, this is the initial concept which I have used, it is sigma 1, 2, 3, 4, 5 and 6. Here instead numbering will going to take the axial representation of the bond formation. Sigma x, sigma minus x, sigma y, sigma minus y, sigma z and sigma minus z. So that is the way we're going to consider this kind of interaction. Sigma bonding in octahedral complex. Each of 6 ligands has a filled p sigma orbitals. Thus we have 6 ligand p orbitals. These p sigma orbitals are laying on x, y and z axis. Hence these p sigma orbitals have been represented as sigma x, and opposite to sigma x, sigma minus x, sigma y opposite to sigma y, sigma minus y, and sigma z opposite to sigma z, sigma minus z. This is the pictorial presentation of the same. You can see here this is s orbital and all the ligands is going to interact with s orbitals. As you know that s orbital is spherically shaped and it's distributed in all the direction in equal proportion, and that is how ligand 1's interaction with this 2, 3, 4, 5 and 6. This interaction of p sigma orbital of ligand 1 with metal orbital represented as plus sigma x or sigma plus x. At the same time, the opposite direction, this ligand 3 has interaction, p orbital, p sigma orbital of ligand 3 has interaction with s orbital, and that is represented as sigma minus x. Similarly, we have sigma plus y, sigma minus y, and sigma plus z, sigma minus z. So this 6 interaction of p sigma orbitals of ligand group and its interaction is represented over here. Different steps involved in the formation of sigma molecular orbital in octahedral complexes. First step is to make a selection of metal ion orbital which are suitable to overlap with ligand p sigma orbital combinations along plus or minus x plus or minus y plus or minus z axis to form sigma molecular orbitals. Likewise, in the previous presentation we discussed that in a first step we need to identify valence orbital of central metal ion. We need to assign irreducible molecule terms to the valence orbital of central metal ion. Here the first step is to make a selection of the metal ion orbitals which are suitable to overlap with ligand p sigma orbital combinations along plus or minus x-axis, plus or minus y-axis, and plus or minus z-axis to form sigma molecular orbitals. The second step involved in the previous presentation, we studied that the second step is to form LGO. Here the second step is to determine the ligand p sigma orbital combination. That is also one kind of LGO, ligand p sigma orbital combination, which may overlap with suitable metal ion orbitals along plus or minus x-axis, plus or minus y-axis, and plus or minus z-axis to give sigma molecular orbitals. Now step 3, in which we study how to generate molecular orbital. Here is the same thing would be there. Third step is the final step. In this step, metal ion orbitals and ligand orbital combinations having the same symmetry overlap with each other, and due to this overlapping it result into sigma bonding orbital formation, that is sigma BMO, and sigma anti-bonding molecular orbital, that is sigma star ABMOs. So the third step will indicates the overlapping between the p sigma orbital of LGO, that is ligand group orbitals, which have same symmetry match with the valence orbital of central metal ion, and this overlapping result into equal number of BMOs and equal number of ABMOs. Sigma BMOs Sigma BMOs Sigma BMOs are generated when metal atomic orbitals and ligand orbital combination combine together with maximum positive overlap, and sigma star, that is anti-bonding molecular orbitals, are formed when the combining orbitals overlap together with maximum negative overlap. That means where positive overlap it result into BMO formation, and if there is a negative overlap that result into uh, anti-bonding molecular orbital, that is ABMOs. Step 1, to make a selection of metal ion orbital suitable for sigma bonding. We know that the valence shell of first transition series, that is 3D metal series, metal ions has 9 orbitals, such as 1 for s orbital, 3 for p, say for example 4 px, 4 py, and 4 pz, and 5 3d, that is 3d z square, 3d x square minus y square, 3d xy, 3d yz, and 3d zx orbitals. 6 of these 9 orbitals, namely 4s, 4px, 4py, and 4pz, along with that 3d z square and 3d x square minus y square. These 6 out of the 9 orbitals have their lobes along the 3 axes x, y, and z. So their lobes spread on axial side direction. 3D xy, 3D yz, and 3D zx orbitals have their lobes in between the axes. That means they are planar orbitals from the metal side. Since 3D xy, 3D yz, and 3D zx orbitals do not have their lobes along axes, these orbitals are not capable of forming sigma bond because they are far away from the interaction with p sigma orbital of LGO, and therefore that interaction will not result into sigma bond formation over here. According to the group theory, the metal ion orbitals are designated by the following symmetry symbols. Mulliken symbols. We have one part as orbitals, the other is a symmetry symbols, and that symmetry symbols is nothing else, is some Mulliken irreducible terms assigned to the valence orbital of central metal ion. For S is assigned by A1G, either small or alphabet capital A1G. For Px, for Py, and for Pz is represented by irreducible term as T1U, 3D z square and 3D x square minus y square, that is doubly degenerate, represented by EG, and 3D xy, 3D yz, and 3D zx represented by T2G. A1G represent a single symmetric orbital, and as I said, single symmetric orbitals means what? You know that for S orbital is a spherical in shape, it's spread uniformly in all the axes equally, and therefore it is a single symmetric orbital which is non-degenerate. EG represents two degenerate orbitals, while T1U represent triply, three degenerate orbitals. T2G is also represent triply degenerate orbitals, but it acts as non-bonding molecular orbital. The subscript G stands for zeroed and U stands for unzeroed are used to indicate whether it is centrosymmetric, that is even, or non-centrosymmetric, that means uneven respectively. So where there is G is applied, it is zeroed, that means centrosymmetric or even, and where there is U applied, then it is uh, non-centrosymmetric, that means uneven. So that way we can represent these symmetry terms. 6 metal ion orbitals. This is the first one. For S, that is A1G, and as already I have told you that it spread in all the axes equally, so that is positive overlapping in all the direction. While here you can see that for Px, the lobe spread on x-axis. This is plus side lobe, this is minus side lobe. Here plus and minus is not a mathematical term. It will just indicate that this is this side of the zx, and the negative lobe is this side of the zx. But the lobe is spread on this uh, x plus side and minus side. Cartesian way we have represented this for x. Similarly for Py, plus side and minus side, and for Pz, plus side and minus side. 3D z square has this plus lobe spread on z, and this minus negative charge spread on this. This is not plus and minus as a positive or negative charge, but the minus indicates in the all direction, while plus lobes spread on z axis. Similarly, x square minus y square, where lobes will spread on x and y axis. On x-axis both positive sign would be there, and on y-axis both negative sign would be there, and that is how it is represented, x square minus y square. So this is the orientation of d orbital, and these are the symmetric terms associated with the valence orbital of central metal ion, 6th valence orbital of central metal ion. From this above discussion, it is clear that out of 9 atomic orbital of central metal ion, only 6 atomic orbitals, such as for S, for Px, for Py, and for Pz, 3D z square and 3D x square minus y square, are suitable orbitals which can overlap with ligand orbital combination to form sigma BMOs and sigma star ABMOs. Now the step 1, we have identified valence orbital and assigned terms, and see the orientation of valence orbital of central metal ion and its degeneracy as well. Now in step 2, we need to determine ligand p sigma orbital combination, and in the previous lecture this step is LGO formation. So this determination of ligand p sigma orbital combination is nothing else, is just LGO formation, but here Cartesian coordinates is taken into consideration. Ligand p sigma orbital combinations are also called by other names, such as group ligand p sigma orbital, that is LGO, composite ligand p orbital, that is also LGO, and ligand symmetry orbitals, that is also a form of LGO. The 6 ligand p sigma orbitals are called as sigma x plus x, that is sigma minus x, sigma plus y, sigma minus y, sigma plus z, and sigma minus z combined together linearly to form 6 ligand p sigma orbital combinations. These ligand p sigma orbitals combinations are designated as sigma s, sigma x, sigma y, sigma z, sigma z square, sigma x square minus y square. This indicates this is a sum of both the side plus and minus together in one form. Now these 6 ligand p sigma orbital combinations have been shown in this figure. One is the s orbital, that is A1G symmetry. You can see that metal, and here the spherical lobes is there, and all positive is directed to the metal side. So we're going to have sigma plus x, sigma minus x, sigma plus y, sigma minus y, sigma plus z, and sigma minus z. That all together indicate sigma s, that is A1G, that is one non-degenerate interaction. Now we have T1U, that is triply degenerate, in which you can see that the lobes of ligand p sigma orbital positive and negative interacted towards metal side, and that way we are going to represent the interaction between metal and ligand. Similarly, this is in y direction and this is in z direction. So these three represent triply degenerate T1U symmetry. While here dz square is there, so all these 6 ligands, you can see that this 2 is directing a positive pole towards the metal, and this 4, which is planar, will indicates the negative pole towards the metal ion, and that way this interaction between metal and LGO is going to be considered later on. And here in x square minus y square, sigma x, sigma minus x, sigma y, and sigma minus y, and different direction plus or minus symbols is directing towards the central metal ion, and that interaction should be considered later on. Now this 6 ligma these 6 ligand p sigma combinations in their normalized form can be written as, now normalized form, that means now we are going to form MO. So in a normalized form, this is summation s, sigma s, that is represented by 1 under root 6 sigma plus x plus y plus z minus z, but all have positive interaction, all have positive. So this represent positive interaction, this represent only the direction, only the orientation. This will not represent plus or minus as mathematical plus or minus value. This will represent the orientation, that the lobes on this side of the x orbital, and this is on the opposite side of the x orbital, and same way in y and z. So this is the normalized wave function associated with the interaction of p sigma orbital with the 4s orbital of central metal ion. Similarly, we have for px and for py and for pz, these three, where you can see that where the positive interaction is towards sigma plus and negative lobes directed towards sigma minus, and that you can see in the above picture as well. I will let you know that here also, that means plus side, that is for sigma positive, and minus lobe is towards sigma negative. So that the same thing you can see over here, plus lobes is towards sigma positive and minus lobes is towards sigma negative. And similarly for y and z, and much in the same way it is for sigma z square, that is 1 under root 12 minus 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 minus, that means all the planar lobes are minus and axial lobes would be positive in sign. So that you can see in the previous slide as well. For z, you can see here all the planar would be a minus symbol, and on this z 2 would be on a plus symbol. So that we can see over here in z square. Similarly, for sigma x square minus y square, the normalized wave function would be 1 by 2 sigma plus x plus sigma minus x. These are two positive and two negative loops interact with the central metal ion of the valence orbital of the central metal ion to form MO. These combinations are represented by group symbols. The metal ion orbitals and the ligand p sigma orbital combination that can be combined together to form sigma BMOs and sigma star ABMOs are also given with this symmetry symbol. You can see the tabular form where metal orbitals are there for S, for Px, for Py, for Pz, 3dz square and 3dx square minus y square. This is ligand combination where sigma S, sigma x, y, z square, x square minus y square and z square, and that can be assigned by the symmetry group. We know that the 3D XY, YZ and ZX orbital have T2G symmetry symbol, and now since there are no ligand orbital combination with T2G symmetry, this 3D XY, YZ and ZX orbital do not participate in the formation of sigma BMOs and sigma star ABMOs. Now step 3, formation of sigma molecular orbital in octahedral complexes. For the formation of molecular orbital requires the following conditions. What the conditions are? Number 1, the combining orbitals should have the same symmetry so that the additive combination of orbitals may allow the maximum overlap of orbitals. It means that when the symmetry is similar for the orbital participate or involve in overlapping, then additive combination of orbitals result into bond formation, and that will going to produce BMOs. Similarly, when the combining orbitals should not have large difference in their energy, they also participate in the overlapping. Now let us apply the above rules to explain the formation of sigma MO molecular orbitals in octahedral complexes. In octahedral complexes, sigma molecular orbitals are formed by the overlap of 6 ligand p sigma orbital combinations with the 6 metal ion sigma orbital along the axis. According to group theory, the ligand p sigma orbital combinations and metal ion orbital which combine together to form molecular orbitals must have the same symmetry. If the symmetry will not match, overlapping is not possible. You need to keep it into mind. This is not a simple inorganic molecule where LCAO will work out. Linear combination of atomic orbital will not work out over here. Here the metal and ligands orbital should match by its symmetry. Then and then their overlapping is possible, combination is possible. We have already shown that since in octahedral complexes 4s orbital of metal ion and sigma s ligand orbital combination have the same symmetric symbol such as A1G, the combine together to form one A1G. Bonding molecular orbital known as A1G BMO and anti-bonding molecular orbital known as A1G star ABMO, and we can see in the next slide these pictures, this overlapping as well. A1G BMO can also be represented as sigma S, and A1G star ABMO can be represented as sigma S star. S stands for S orbital. So that you can see A1G combined together to form one BMO A1G and the other A1G star ABMO, that is anti-bonding molecular orbital. Here you can see that this energy level difference, and that you need to keep in mind. This is not a design. 4s orbital is little higher in energy compared to ligand group orbitals, sigma s orbitals. That is lower in energy. That means this will remain closer to BMO and this will remain closer to ABMO. That means BMO represent ligand characteristic while ABMO represent metal characteristic as well. and this is 4s orbital of central metal ion, and this is the ligand p sigma orbital, and their combination result into BMO and ABMO. So this is a formation of A1G BMO, that is sigma s, and A1G star ABMO, that is sigma star s, in octahedral complexes. Next, now the 3p 4p orbitals such as 4px, 4py and 4pz, and 3 ligand sigma orbitals, say for example sigma x, sigma y and sigma z, have the same symmetry, that is T1U symmetry, and they combine together to form 3 degenerate T1U BMO and T1U star ABMO, we can see in our next slide. T1U set of 3 degenerate BMOs can be represented as sigma p, and T1U star set of 3 degenerate ABMO can be represented by sigma star p. The 3 degenerate molecular orbital of T1U, that is sigma p set, are represented as sigma x, sigma y and sigma z, whilst the 3 degenerate MOs of T1U star, that is represented as sigma p star set, can be represented as sigma star x, sigma star y and sigma star z. So this overlapping will result into bond formation. Now since the 3 4p orbital and 3 ligand sigma orbitals combine together to form T1U symmetry, T1U BMOs and T1U star ABMO, we can see here in the figure. Here also you can see that the atomic orbital of central metal ion, that is 4p, is higher energetic compared to LGO, p sigma orbital of ligand group. That means p sigma orbital of ligand group remain closer to uh, the BMO orbital, and 3 sigma star, that is closer to atomic orbital of metal ion. That means this will represent some ligand characteristic, while this have some little we can say metal characteristic as well. This is formation of 3T1U BMO, that is also represented as sigma p, and 3T1U star ABMO, which is also represented as sigma star p. Now since 3d z square and 3d x square minus y square orbitals and 2 ligand p sigma orbital combination will have sigma z square and sigma x square minus y square have the same symmetry. Already we have told many a time that without similar symmetry there is no interaction, and here you can see that both have same symmetry, so they are going to interact with each other and going to give two kind of molecular orbital, BMO and ABMO. E.g. set of 2 degenerate BMO represented as sigma D, and similarly E.g. star set of 2 degenerate ABMO is represented by sigma star D. 2 degenerate molecular orbital of Eg, or we can say sigma D set, are represented as sigma z square and sigma x square minus y square. Similarly, 2 degenerate molecular orbital of sigma Eg star or sigma star D set are represented as sigma z square star and sigma x square minus y square. Star is missing over here, that you need to mention. Now formation of T1U molecular orbital, bonding molecular orbital, that is sigma p, and T1U star anti-bonding molecular orbital, that is sigma star p. So this is 3dz square and 3dx square minus y square, and that combination here also you can see that atomic orbital is little higher in energy comparing with the LGO of the same symmetry, and because the symmetry is similar, although there is a little energy gap, energy difference, they interact with each other, that is a positive interaction, and it result into BMO formation and ABMO formation. BMO formation is represented by sigma z square and sigma x square minus y square, while ABMO is represented by sigma star z square and sigma star x square minus y square. These are the 4 molecular orbital, 2 of them which is BMO and the rest 2 of them will be ABMO. the BMO remains closer to the LGO, so they will represent the characteristic of ligand, while ABMO remain closer to the AO of a metal, and therefore it represent the metallic characteristic as well. Now this is the entire table indicating the combination of 6 ligand p sigma orbital, and it's going to form 6 sigma BMO and 6 sigma star ABMO, and this is the pictorial as well as the sigma representation of the overlapping. A construction of MOED, molecular orbital energy diagram. A1G, that is sigma S, and A1G star, that is sigma S star, is a non-degenerate molecular orbital. It is singly degenerate orbital. T1U and T1U star, that is triply degenerate molecular orbital. Similarly, EG and EG star is a doubly degenerate molecular orbitals. Metal ion orbitals 3D XY, YZ and ZX are represented as T2G. They can also be represented as pi d orbital as well, because they are in a planar side. They do not have direct interaction with LGO. And later on we're going to learn that how they will contribute in pi bond formation. These are non-bonding atomic orbitals and they are triply degenerate. Since all the molecular orbital mentioned above are formed by the overlap along the axis, all these MOs are sigma MOs. Above discussion shows that the combination of 6 metal ion orbitals like 4s, 4px, 4py, 4pz and 3dx square, 3dz square and 3dx square minus y square with 6 ligand p sigma orbital combinations, namely sigma s, sigma x, sigma y, sigma z square and sigma x square minus y square gives 6 BMOs and 6 ABMOs. 6 BMOs are A1G, that is 1, T1U, that is 3 and EG, that is 2. And 6 ABMO are A1G star, that is 1, T1U star, that is 3 and EG star, that is 2. Now construction of ABMO includes the lobes of triply degenerate 3DXY, 3DYZ. This is a typological mistake. You need to consider 3DYZ and 3DZX orbital do not lie along the axis. These orbitals do not participate in the process of the formation of sigma molecular orbitals. These orbitals remains in a non-bonding and hence are called non-bonding orbitals. This can however overlap sidewise with the filled or unfilled p orbital of the same 6 ligand p orbital are those which are capable of forming metal ligand pi bond and form metal ligand pi bond or pi molecular orbitals. Thus, these orbitals are generally referred as p, PD, DP or PXY, PYZ or PZX orbitals. This is the nomenclature of this pi orbital. The formation of 6 BMOs and 6 ABMOs and 3 non-bonding 3D orbitals, that is 3D XY, YZ and ZX, which have the same symmetry or same energy level with the atomic orbital of transition metal, and they will purely indicate the metallic characteristic as shown in this figure, which is commonly known as molecular orbital energy diagram, MOED. So here you can see the MOED for octahedral only sigma donation. Now please student keep in mind about the energy differences. Lowest most is A1G bonding BMO. Upper to that T1U, that is 4x, 4px, 4py, 4pz. Above that EG, that is 3dz square and 3dx square minus y square. Above it the sigma p orbital represented as sigma s, sigma x plus sigma y plus sigma z square plus sigma x square minus y square. And above that atomic orbital of transition metal 3D, that is 3dx square minus y square, 3dz square, 3dxy, 3dyz and 3dzx. And at the same energy level we have 3 non-bonding molecular orbital, that is T2G, and above it we have 4s of A1G symmetry, above which we have EG above which we have for px, for py, for pz, that is AO T1U symmetry of the central metal ion, and above which we have antibonding T1U star and the highest energetic, that is A1G star. You need to represent MO in this energy order only. If the energy order get changed, you won't get the marks for that. That you need to keep in mind, friends. Now let's learn the pictorial representation of these metal ion valence orbitals and p sigma orbital of LGO with each other. Pictorial representation of the formation of A1G1, A1G star 1, T1U3, T1U star 3, EG2 and EG star 2 molecular orbital is given in figure 1, 2 and 3. A1G, T1U and EG are BMOs, A1G star, T1U star and EG star are ABMOs. Here, this is the first interaction with A1G, and you can see that this is a positive interaction. So this is going to form your BMO. This is negative interaction, so it's going to form your ABMO. Plus and minus is not for mathematical value plus and minus, it is for BMO and ABMO respectively. So this is A1G and A1G star. Second one is for T1U, 3T1U and 3T1U star. This is the interaction, pictorial interaction is shown. Here you can see that positive interaction, and here the negative interaction is there, and that is why in that one we have written as the normalized wave function or molecular orbital wave function as 1 under root 2 plus sigma x plus x and minus sigma minus x. So that is how it can be represented as T1U BMO, and negative, the opposite, yeah, minus minus, that is positive interaction, plus plus, that is positive interaction, but plus minus, that is negative interaction, plus minus, that is negative interaction. So this plus plus and minus minus will going to form BMO, while plus minus is going to form ABMO. Much similar is there for y and z axis as well. Now for EG, BMO and ABMO, here also you can see that minus is going to interact with minus. For planar, minus is going to interact with minus and plus is going to interact with plus, that is positive interaction, and that going to form BMO EG, while here plus is going to interact with minus and plus is going to interact with minus, so this will going to give AG star ABMO. Similarly for x square on minus y square, this plus and plus, minus and minus is going to interact with each other, that is a positive interaction, and it's going to form EGBMO, and plus minus, minus plus, it's a negative interaction, result into EG star ABMO. That's enough from my side. Thank you for listening very unwearingly, and I would like to read the quote by Pope Francis that teaching is a beautiful job. It allows you to see the growth day by day of people entrusted to your care. It is a little like being parents. At least spiritually, it is a great responsibility, and I feel today in this lockdown period how much great responsibility this teaching is. Thank you very much, friends, for paying attention to my lecture.